Bismillahirrahmanirrahim. This is lab number 10, construction of electronic analog meters, and we are going to discuss the construction of electronic DC voltmeter in specific. So our objective is to study fundamentals of electronic analog meters, and we intend to design and construct electronic DC voltmeter. This is the circuit that is supposed to be utilized for construction of electronic DC voltmeter. As you can see that this particular circuit makes use of a potential divider in between the terminals 1 and 2. This potential divider consists of three resistors. One is of value 800 kilo ohms, the second one of 100 kilo ohms, and the third one is also of 100 kilo ohms. We are designing this electronic DC voltmeter for three ranges, that is 1 volt, 5 volt and 10 volts correspondingly, and these values of resistors are selected in such a way that for all values of ranges we get 1 volt as input of the op amp. Since we are using op amp in its non-inverting mode, so the gain equation is given by 1 plus R2 over R1. The value of R2 and R1 are correspondingly 90 kilo ohms and 10 kilo ohms. So these values will give us a gain of 10. Since we are constructing this electronic DC voltmeter for three ranges, that is 1 volt, 5 volt and 10 volts, which means that once we are using for the 1 volt, we will directly get 1 volt as an input of the op amp. For the 5 volts, we will get 1 volt as the input in a way that 4 over 5 of the total voltage, that is 5 volts, will dissipate across the 800 kilo ohm resistor. The remaining 1 volt will act as an input voltage to the op amp. Similar will be the case for the third range, that is 10 volts. In case of 10 volts range, 9 by 10 of the total voltage, that is 9 volts, will appear across 800 plus 100 kilo ohm resistors. Remaining 1 volt will act as an input to the op amp. So for each range we are having 1 volt as an input of the op amp, and this input is 10 times amplified by the op amp. Resultantly, we are getting 10 volts at the output of the op amp. Now this 10 volt is to be dissipated across the PMMC. The value of the resistor that is connected in series with the PMMC will depend upon the PMMC that is being used. For this case, that is in the figure, for PMMC having the IFST equal to 200 microampere, we need to connect 50 kilo ohm resistor in series with it in order to equate 10 volts of the voltage that is appearing across the output of the op amp. For practical purposes, we'll use our practical values, that is we'll be designing PMMC with IFST equal to 0.3 milliampere and internal resistance equal to 100 ohms. So this is what we just discussed, that is 10 volts is appearing across the output of the op amp, and this 10 volt is to be dissipated across the PMMC. The value of resistor is calculated in such a way that the current flowing through PMMC is equal to IFST. So this is the practical case that we'll be utilizing since we are making use of our PMMC. So we'll first of all work out the value of total resistance that is supposed to be connected in series with the PMMC. Since the output will always be equal to 10 volts, so this 10 volts is divided by the IFST 0.3 milli to have the total resistance equal to 33.3 kilo ohms. We have PMMC having the internal resistance equal to 100 ohms, so the value of the resistor that is in actual supposed to be connected in series with PMMC, that is RS, is 33.2 kilo ohms. So these are the values for our experimental cases. How will we be reading the scale with respect to voltage ranges? The lower scale, as you can see, represents the values of currents that is flowing through PMMC. So for maximum value of IFST, we'll have the 1 volt maximum for 1 volt range, 5 volt maximum for 5 volt range, and 10 volts maximum for 10 volt range. Similarly, half of the full scale deflection current will correspond to 0.5 volts of the 1 volt range, 2.5 volts of the 5 volt range, and 5 volts for the 10 volts range. This is the experimental setup. This particular source is for the applying input. These two sources are for the plus VCC and minus VCC, since we are making use of an op amp, and resultant circuit is there on the breadboard, which is connected to a PMMC. So this is the close-up of the circuit. As you can see, we have used three resistors as specified earlier in the circuit diagram: 800 kilo ohms, 100 kilo ohm, and 100 kilo ohm, and the corresponding ranges 1 volt, 5 volt, and 10 volts voltage range. These resistors are 90 and 10 for obtaining the gain equal to 10, and the value of resistor that was supposed to be connected in series with PMMC is 33.2 kilo ohm, which is connected here. The yellow line that you see, this yellow wire that you see, is the selector switch. So at this particular moment it is at 10 volts range, so it can be moved to correspondingly 5 volts and 1 volt range as desired. This is another closer view of the circuit. So you can see the pins 1, 2, 3, 4, 5, 6. We are getting the output across the pin number 6, and this goes to the RS, that is 33.2 kilo ohms. This particular wire is to minus VCC, this one is to plus VCC. This yellow wire is the range selection wire, which is to be connected to different ranges, that is 1 volt, 5 volt, and 10 volts correspondingly. So this is the experimental setup. We are applying the input voltage of 10 volts. We have set VCC equal to 10 each, and the selector switch is at 10 volts selection. Since we are applying the input as 10 volts and the range is also at 10, so we must see the full scale deflection. So it is approximately the full scale deflection when we have applied the input voltage equal to 10 volts. So here we are applying the 5 volts plus VCC and minus VCC is equal to 10. Selector switch is at 5, and we are having approximately full scale deflection. The difference in the values is, or the deflection is, because of the use of approximate values of resistor. The resistors are not accurate. If we apply 5 volts, keep VCC as 10 plus VCC and minus VCC, when the selector switch is at 10, we must see half scale deflection. Since we are at the selector switch 10 volts and we are applying 5 volts, so it must correspond to half scale deflection. So this is what is cross verified here. These are the values, these are the experimental observations that are supposed to be considered. So for VFST equal to 10 volts, this is the voltage that is appearing across the output of the op amp. For VFST equal to 10 volts, we knew that our IFST is supposed to be kept as 0.30 milliampere, and we know RM was 100 ohms for our PMMC. So the total resistance came out to be 33.310 kilo ohms, and subtracting RM from the R total was the value of resistance that was actually supposed to be connected in series with PMMC for our case. The gain was supposed to be kept equal to 10, since we made use of 90 and 10 kilo ohm resistor, and the gain equation was 1 plus R2 over R3. Similarly, these values were cross verified. These are the calculated values of resistors and voltages. These are correspondingly calculated values, practically seen values of a resistor and the voltages. Thank you.